So what we're going to talk about today is an intro into our next topic. We'll leave that off for a second. So we just finished talking about projectile motion, right? So here is a projectile, and I'm going to draw a couple of vectors here to represent the velocity vector at a couple of places along that motion. At every place along that motion, the velocity vector is tangent to the curve, right? We said that was true. Now, at all points during the motion, though, that velocity vector is changing because the object is accelerating, and it's accelerating downwards. Therefore, throughout the motion, the relationship between that velocity vector and acceleration vector was changing over time. Right? Just trying to draw that acceleration vector in the same direction each time, the velocity vector changing. And the reason why that was changing was because there was a component of velocity that was perpendicular to the acceleration, and this was causing a change in direction. But there was a component of velocity that was along the same axis as the acceleration, which is why this object was slowing down when the velocity and acceleration were antiparallel, and speeding up when the velocity was in the same direction as the acceleration. That's what we saw in the last unit, projectile motion. Now, what we're going to do today is look at a different type of non-linear path, and we're going to look at something that's called uniform circular motion. So, little different than what we were just talking about. So what I think would be very helpful for you, I have my keys here. I'm just going to tie a string to my keys because I'm going to whirl the keys in a circle over my head. And you should do that too. Like if you have a piece of string, tie them to keys. You need something that has a little bit of heft to it, right? And what I want you to do is just find some place where you're not going to hit into anything and twirl the keys in a circle that is in the same plane as the ground over your head, okay? Right? So what's uniform about this circular motion? Well, I can have the uniform circular motion if I hold two things uniform. So for something to be in uniform circular motion, what we're going to have here is something that has a constant radius as well as have a constant speed. Now, notice here, I said the word speed. Why would I not say constant velocity? So write yourself a note. I'll stop the video. Write yourself a note. Why not constant velocity? Hopefully what you said to us that this is false because the direction of the velocity vector, oh God, is always changing, right? And velocity being a vector means that and acceleration being a vector means that if you have that velocity vector changing, there is an acceleration. So, uniform circular motion, constant radius, constant speed. Another way you could say this is not just constant speed then, but then I could also say constant period. I want to make sure we define that, right? Period being the amount of time to make one circle. Okay, And I'm going to give this symbol, sort of a crazy looking T with little wings there, capital T with little wings, as our symbol for period. So anything in uniform circular motion is going to have a constant radius, a constant speed, and a constant period. So there we go. So let's say we're looking at you twirling your keys over your head, and we're looking at an overhead view, right? And so what we would see then is a circle. Not bad for a freehand circle, not great, but there it is. Let's say that from this perspective, our keys were going around counterclockwise, so around like this. At this location in space, we would draw in the velocity vector like that, right? Tangent to the circle. Here, it would be there, tangent to the circle. Here, tangent to the circle, so on and so forth. Okay? Now, here's the thing though. If that velocity vector is constantly changing in directions, therefore it must be accelerating. So we have something that is also now true about uniform motion, is that because the direction of the velocity is constantly changing, the object must be accelerating. Okay? Why do I know that's true? I know that's true because of Newton's first law. Let's remember what Newton's first law tells us. It says a body in motion will remain in motion at a constant speed in a straight line unless acted upon by a net external force. So since our object is not going in a straight line, there must be an external net force, which means by Newton's second law, it must be accelerating. So we could also say, therefore, this object must be experiencing a net force. And this net force, very specifically, is one that is causing it to change its direction. So if you go back to twirling your keys over your head, I'm doing it myself here, right? Think about, well, what is the force that's acting on the keys that's causing it to change in its direction? Well, because I have a string attached to it, that force must be the tension force. Now, what direction does that tension force act? Well, here on this object, this is not a free body diagram, mind you, it's just a diagram. That tension is acting like this, right? Because here I am holding it, and we know that tension always pulls away from the object in question. At this location, the tension must be pulling like this. In this case, the tension is pulling like this. Notice, at every point, the tension here is remaining perpendicular to the velocity. And in this case, the net force here is that tension force because there's no other force acting that we can see. Now there is gravity acting, but gravity is acting into the page since this is an overhead view, and therefore it's in a totally different dimension. So what does that mean for us? Well, a couple of really interesting things here. Notice, actually, let's go back to that. If in this case, the tension is the net force, therefore the acceleration must act along the tension, because accelerations always act in the direction of the net force. So here we go, I'll put in my acceleration. And that should make sense now, because if you notice, at all points during this motion, the velocity is perpendicular to the acceleration. And based on the work we said before, that means that that acceleration is changing the direction of the velocity, not the magnitude of the velocity. Okay, and so that's what we have here. We need a force that acts perpendicular to the velocity in order to change its direction. Now, unlike in projectile motion, where because the force was in this constant direction downwards, that the velocity was changing the angle between the velocity and the acceleration constantly, causing a change in speed and a change in direction. Here, as it's going around the circle, the tension is always pulling inwards, the velocity is always perpendicular, meaning that there's a constant relationship between the direction of the velocity and the accelerations remaining perpendicular, which is why we're getting this uniform circular motion. All right, cool. So what I want to do here is define then a new direction, okay? Because if I were to ask you, well, what direction is this tension acting? You might be tempted here to say, well, like if we do our normal like Cartesian, right? That this is positive x and this is positive y, saying that like, oh, it's negative x, then it's like negative x, negative y, positive x, negative y, positive x, so on and so forth. That's not very helpful in this case. We're going to define a new direction, a new dimension called the radial axis, right? And so the radial axis is an axis that goes directly into and directly out of the circle. And so, like for example, that would be the positive r-axis. This is the negative r-axis. But when the object is, say, over here, that's the positive r-axis, and that's the negative r-axis. You'll note that it is locally perpendicular to the tangent line there, right? And so what you'll notice here is that our net force always acts radially inwards. Okay? And that's going to be true for anything that's in uniform circular motion, that you're going to need a net force to act radially inwards to change the direction of the velocity without changing its magnitude. Okay? And so let's just talk about examples of that. Like, so here we have the string, right, on your keys causing that. If you think about the moon in its orbit, you have gravity pulling the moon towards the Earth, acting radially inwards. If you think about a car going around a corner, right? So here's a car going around a corner. What force is going to cause the car, once again, overhead view, what force causes the car to go around the corner? Well, in order to turn your car, what you do is you turn your car wheel, right? So let's actually, we're going to look at this even a bit more. So we know we turn the car wheel, you turn it inwards. Because if you do nothing, an object in motion would remain in motion at a constant speed in a straight line if nothing were to happen. So there must be something that causes the car to go around in the corner. And that something actually is friction, specifically static friction. We'll get to it in a second. Let me actually draw a bigger picture of this. Because let's talk about, let's say you're in the back seat of a car. Let's say it's an old car, like a 1970s Chevy. And if you've ever seen these cars, they have these big back bench seats, right? So here you are sitting there. And if you've ever sat on one of those, the seats are made of like this cheap vinyl, right? They're very slippery. Let's say you're wearing your polyester pants because you're going to a 70s party. So very slippery as well. What would happen as you were to round that corner? Well, as you're going around the corner, so let me just draw the car going around the corner here, that unless there's something causing you to go in the circle, you're going to want to, due to Newton's first law, actually travel in a straight line. Draw this, right? And so if you're wearing your polyester pants, what ends up happening here is, from your perspective, it looks like you are pushed in this direction because you would end up over here, but really what you're doing is traveling in a straight line until something causes you to change direction. And that would be the door here finally causing you to go with the car, right? But it feels like you were pushed to the left as you turned right. Hopefully that inspires something. Hopefully that makes you think, oh my God, fictitious forces. I always misspell this. Fictitious forces. Pardon my spelling there. Right? And that means another proof that we know we are accelerating. And hopefully you remember what direction you're accelerating. You're accelerating opposite the direction you feel the fictitious force. So here, because I felt pushed to the left, I must be accelerating to the right. So this object is accelerating this way. I feel pushed that way, I must be accelerating this way. Once again, verifying that I'm accelerating inwards towards the center of that circle. Now here, without friction between your butt and the seat, you traveled in a straight line. If there were friction, you would travel along that curve with the car. The same thing with the cars and the wheel, that there is friction, specifically static friction, because you're not skidding with respect to the road. When you turn your car wheel in, that creates a static frictional force that acts inwards towards the center of the circle, right? So the point here is that you need a net force inwards towards the center of the circle in order to do that. So in other words, for problem solving, this is going to be something we'll do in a later video or next video, that when we look at Newton's second law here, what we're going to realize is that we're going to have to talk about a new dimension, and that is a radial dimension. So rather than having F net x and F net y, we're going to talk about an F net r equals ma and then r. So this term here is the net force in the radial direction. I'm going to give another name to it in a second. And this is called the radial acceleration. Now, because that net force in the radial direction always acts radially inwards, it's sometimes given a new name. It's sometimes called the centripetal force. Okay? Now some of you are like, no, hold on, there's another word. We'll talk about that other disgusting word later, the one you're thinking of as centrifugal. But let's look at centripetal for a second. So centri, meaning center, P-E-T-A, that is actually a Latin root from the word petare, which means to seek. And so this literally translates as center-seeking force. So the net force in the radial direction is sometimes called the centripetal force F sub c. Now, the reason why I hate that is because it makes people think that the centripetal force is a type of force. It's not, right? It's the net force in the radial direction. So for example, when I twirl my keys over my head, the tension is the net force, it's the centripetal force. Gravity for the moon, pulling the moon in the orbit around the Earth, is the centripetal force. The static friction pulling you around a corner when you're in a car is the centripetal force. Now, in more complicated problems, there might be multiple forces acting along the radial line, and therefore their vector addition is the centripetal force, right? So it's not just one singular force, it's just another example of a net force. Now, the radial acceleration is also called then the centripetal acceleration. Okay, the centripetal acceleration, which some people say AC. Now, here we're going to have a new equation for the centripetal acceleration, because if we think about our old acceleration equation, delta V over t, that's V final minus V initial over t, but if I say, for example, I'm going around my circle at a constant speed, you'd be very tempted to want to put the same value in there. But remember, this is vector, and then I would have to do this weird vector subtraction between these two things in order to find that. That's not a very helpful way of doing it. So this is going to be our equation for what we're going to call a linear acceleration. But for a centripetal acceleration, it's not as useful. So the centripetal acceleration can be defined as the rate at which the direction of the velocity changes whereas the linear acceleration is the rate at which the magnitude of the velocity changes. So I need a new equation for this centripetal acceleration. I'm going to kind of assert it to you, but then we'll kind of go through it. So it'll hopefully make sense. The centripetal accelerations equation is going to be whatever the tangential speed is squared divided by the radius. I'm just going to box that, okay? AC equals VT squared over R, right? And these are the VTs, the tangential acceleration speeds. So why that? Well, if we think about that, if it's the rate at which direction changes, the faster I go around this circle, right? Therefore, the more the direction changes over time, right? If I go faster around it, I go through a full change of 360 degrees in less time. That would make sense then that I would have a greater rate of change in direction. Now, why smaller radius? Well, if you think about that, if I'm going the same speed around this smaller radius, right, I can change direction by 90 degrees a lot quicker than I can change direction by 90 degrees here, just because that arc length is smaller. And so that's the rationale for why the centripetal accelerations equations, that the derivation of that is actually rather complicated. We're not going to get into it. All right, there's one last piece that we need to know for this before we start getting into some problem solving. And that's actually talking about this tangential speed. Well, I need an equation for it, right? Because if I think about this, I don't really think about velocities, because once I go around a circle once, my velocity has changed and I'm back to what I was before. So my change in velocity would be 0 once around the circle. Not very helpful there. So I can't do this by normally doing like displacement over time, because my displacement is 0 over the time. So instead, let's think speed, let's think distance over time. Well, what speed am I talking about? Well, what distance am I talking about? Well, I'm talking about the circumference. So as long as I'm going at uniform circular motion, the circumference here is a regular feature, 2 pi r. And the time to do one circumference is by definition 1 period's worth of time. So there we go. Because we're constrained to uniform circular motion, here's our expression for the average, average speed or the instantaneous speed, the tangential speed as you go around that circle. There is your centripetal acceleration, and we're going to see how all this comes together to do some problem solving. But let's just bring it back together. Velocity is always tangent, acceleration and net force always acts radially inwards, changing the direction over time. It's true because of Newton's first law, verified everything we talked about, and then we have some equations.